for those who may just be joining us, this is a World Science University masterclass on the dark side of the universe. And I am your dark guide, the dark cosmologist, Michael Turner. I'm a professor of astrophysics at the University of Chicago and the director of the Kavli Institute for Cosmological Physics at the University of Chicago. And we were just talking about infinite universes. So I'm going to go on to the second question. And the second question is from Terrell. And this is a fun one. It's going to allow me to pontificate a little bit here on science. Do you think that the energy in the Big Bang was finite or infinite? So that's a really good question. If we had a finite universe, you might think that the energy in the Big Bang is infinite. But as we go back in time, the energy of the universe rises, and we'll come back to that in a second. So if we could go all the way back to the Big Bang, and that's a very big if, the answer would be infinite. Of course, if we had an infinite universe, I think you all guessed the answer, that in an infinite universe, the energy is always infinite, but we don't know that whether or not we have a finite universe or an infinite universe. So let me just go back to that a little bit about the finite universe, because that may seem to be a little bit puzzling. Shouldn't the energy of the universe be not change with time? And the answer is no. The energy of the universe changes with time, and the energy, the simplest one to see, is the energy in the radiation, in the cosmic microwave background. So indeed, the number of photons, if we focus on a little box, the number of photons stays the same as we watch this box get smaller or littler. But due to the redshift, the energy per photon as we move forward gets lower. And so the amount of energy in that box decreases as the universe expands. So the microwave background, which today is just, you can't even see it with your eyes, it's just microwaves, it's just heat. Way back when the universe was 380,000 years old, it was bright light. And so that's how that works. And then I'll just round out Terrell's question here is, do you think the energy in the Big Bang was finite or infinite? So it really doesn't matter what I think. So that's the wonderful thing about science. It's not authority-based. It's what we find out and what we know. And so my opinion doesn't really count, but I'm just telling you what we know so far. Okay, moving along. This is Christian asks a really, really good question. And sadly, I will not give a really, really, probably not going to give the answer that's going to satisfy everyone. And Christian asks the really, really simple question, what is the universe expanding into? So we talked about the universe being an expansion of space. Space is expanding, getting bigger, the galaxies being carried along. So it naturally raises the question of, what is space expanding into? And the answer is, and if you can understand this, if you can wrap your head around this, you understand half of Einstein's general relativity, or maybe a third. Because Einstein's general theory of relativity says that space is dynamical, it's flexible, so that space can bend or stretch. And the best example of the flexibility of space is the expansion of the universe. The universe is expanding and space is expanding, and it need not expand into anything. So you really don't need it to expand into anything. Enough said. On the other hand, if you would like that crutch, you can create that crutch. So if we're imagining a two-dimensional universe, of course we live in a three-dimensional universe, three space dimensions, at least. Two-dimensional universe might be a rubber sheet, a two-dimensional universe that's a rubber sheet, and we watch that space expand into three dimensions. So from the luxury of 3 dimensions, we watch it expand. And so there we could see it expanding in space. But we don't need anything for space to expand into. And if you can wrap your head around that, you really understand one of the essences of Einstein's general relativity, one of his biggest breakthroughs, which is space-time is dynamical. It's not the fixed space-time that Newton was talking about. Let's see. On to a question, an interesting question from Andrew. And Andrew obviously was watching, I don't know if it was Alan Guth and Andre Linde talking about inflation. Andrew starts by saying, inflation forces the universe to be flat. That's a true statement. Could inflation also be responsible in forcing dark energy to remain constant over time? And Andrew knew that corresponds to equation of state W equal -1. Those of you who don't know about the equation of state, don't worry about that. So really, really interesting question about dark energy. And normally when somebody asks me a question about dark energy and says, could X, Y, or Z be possible? My answer is maybe, because we know so little bit about it. And so I'll say maybe, but then let me expand upon this. So how does inflation force the universe to be flat? Well, if you imagine that, I'll just remind you what Alan said or Andre said. If you imagine that before inflation, the universe had some curvature to it, so space bent, was curved positively or negatively. Then inflation comes along, and the hallmark of inflation is it just makes everything bigger, enormously bigger. And so you know this, that if you take some surface that's curved and you just blow that surface up, imagine a balloon, and you take a balloon and you blow it up, and if you look at a fixed piece of it, as you blow it up, it looks flatter. So that's how inflation makes the universe look flat. Now, whether or not it can do that for dark energy, I don't know. That's a really interesting one. That's the kind of conceptual breakthrough that, because I think what Andrew also knows is that all the data we have is consistent with dark energy remaining constant over time. We haven't measured that very well, only to a precision about 5 or 10%. And of course, dark energy being constant over time corresponds to dark energy being the energy of the quantum vacuum. And so that's an interesting thought to pursue, Andrew, but I'm not quite sure how to put equations to it. Okay, we'll go on to number 9. I really enjoyed all of these questions. So Richard asks, we think of the speed of light as being constant in a vacuum, but if dark matter and dark energy are scattered throughout the universe, they indeed are. Is it still truly a vacuum? Does this have any repercussion on how we consider the constancy of the speed of light? Oh, you got a bunch of stuff. I need to unpack that for you. So the speed of light is, as far as we know, a constant of nature. And it's that 300,000 kilometers per second. So dark energy is almost uniformly distributed throughout space. We see no evidence that it clumps up. Dark matter, on the other hand, does clump up. So where our galaxy is, the abundance of dark matter is about 100,000 times greater than it is in a random spot in the universe. Even in our galaxy, the average density of dark matter is really, really low. Probably better than, certainly better than any vacuum I could create, because I'm not a very good experimentalist, but I bet better than just about any vacuum that anyone could create. But let's go on to the crux of this. Does the fact that the universe is not empty, it's filled with dark matter and dark energy, do anything to the speed of light? And the reason I really like this question is it takes me back to my days when I was a student at Caltech, And one of my mentors, one of my heroes, was Richard Feynman. And I learned physics from the Feynman lectures on physics. And one of the amazing things I learned that I take with me today, if I had a blackboard here, I'd get up there and derive it for you, is that light always moves at the speed of light, somewhat contrary to what you learned in high school physics or college physics. Uh, Probably in those classes you learned that in a medium like glass, light slows down, or in matter, light slows down, and in fact, scientists are able to create mediums where light slows down by an enormous amount. And Feynman taught me, and I think all of us, how to correctly look at this. So it's not so much that light is slowing down. It's not really slowing down, but it's moving through a medium where that's made of electrons. And light is an electromagnetic wave that shakes those electrons. And if you shake an electron, it radiates more light. And now you add the original light plus the re-radiated light by the electrons, and the wave is different. And the wave appears to move slower or sometimes faster than the speed of light in vacuum. But the speed of light is constant. What's happened here is that you've just added some more light, and so it's changed the situation. The resultant light, the sum of the light that was coming in plus the light that was radiated by the electrons, creates an electromagnetic wave that looks like it's moving slower than light. But light always moves at the speed of light, which is easy to remember. Okay, thank you very much, Richard, for that question. Number 7. Julius asks, you said that we can discount anything made of atoms as making up the dark matter. How were atoms eliminated as a possibility? And that is a really, really, really good question. And so there's an important take-home there. So how did we eliminate atoms as being the dark matter? I'm going to give you absolutely the best evidence, and then I'll talk about some of the other lines of evidence. But sometimes people don't give you the best evidence, which is one of my hobby horses. Sometimes my particle physics friends don't give the best evidence. They talk about, dark matter in galaxies and so on and so forth. But the best evidence, and now I'm going to go to split screen here. I'm going to split the screen so that you can see the cosmic microwave background on the screen. Our best evidence comes from analyzing the small variations in the cosmic microwave background. That cosmic microwave background, those photons are coming to us when the universe is about 380,000 years old. And there is the Planck map of the cosmic microwave background. And this is a map of those small variations in the cosmic microwaves. They tell us what the universe was like at a much simpler time. And let's see, if you can see my cursor, I'm pointing at the best product placement of all time. There's Stephen Hawking's initials in the cosmic microwave background. And of course, we analyze this mathematically using spherical harmonics, but if you don't know what a spherical harmonic, that's okay. And so we're measuring the temperature difference on the sky, that's the up and down axis, as against the separation between 2 points. And we do it in this multipole number. So the high multipoles look at the directions that are separated by a small angle, so out here by arc minutes, and the small multipoles correspond to angles that are separated by a lot. And encoded in these bumps and wiggles that we call the acoustic oscillations is information about the universe. And the height of what we call the first peak is sensitive to the total amount of matter. And it allows us to measure the total amount of matter to very, very high precision. I won't give it to you to the full precision, but the total amount of matter is about 30% of the critical density. The ratio of the height of the first peak, right here, to the second peak is sensitive to the amount of atoms in the universe. And what we deduce from the ratio that we see is that atoms are 5%. And so 30 is the total, 5 is atoms. Even a half astrophysicist like myself knows that 30 is much bigger than 5. So 25 is unexplained. 25% is unexplained because we have a total accounting of the atoms, we have a total accounting of the matter, and they disagree. And so that's why, that's our best evidence that the dark matter is not atoms. Now, I'm not going to show you a slide on this, but we also have evidence, other evidence for the total amount of matter in the universe. The distribution of galaxies in large-scale structure also gives us that 30% number. We also have evidence for the total amount of atoms in the universe that involves work that I did when I was a young postdoc here, and that evidence involves the amount of deuterium made in the Big Bang. And the amount of deuterium in the Big Bang is sensitive to the total amount of atoms, and guess what number you get? 5%. And so that's our best evidence. And now, let's see, I'm trying to remember who, Julius. This is where things get really exciting, because we have this outrageous hypothesis that most of the matter in the universe is something other than atoms, and we have not proven it yet. And we're way out on a limb, and we might even be wrong, which leads us to the question from Gaz. So let's suppose there is no, we like to call it non-baryonic dark matter or exotic dark matter. Do you have something in your back pocket? Do you have a backup theory? And Gaz asks about a theory that I don't like very much, called modified Newtonian dynamics, or MOND. And his question, he says, what are your views? So he's allowing me to pontificate. What are your views on MOND? Is it a respected theory within physics? So let me say a little bit about MOND. MOND in 1983, when it was put forward by Morty Milgram, was a brilliant idea. It was one of those brilliant ideas that could have been, I don't want to reveal that yet. I'm going to hide that for a second. It could have been a very great insight, because the simplest way to not have dark matter would say is as you get farther away from the center of a galaxy, gravity gets stronger, or doesn't fall off as fast as it does in Newton's theory. You might say, oh, okay, yeah, that sounds good. That doesn't work, because the place where dark matter kicks in big galaxies is much further out than where it is in where it kicks in small galaxies. And Morty had this brilliant idea, and his idea is, well, maybe he noticed that the need for dark matter didn't kick in at a particular distance from the center of a galaxy, but at a particular acceleration. And so he said, maybe at low accelerations, everybody knows F equals ma, that's Newton's second law. He said maybe at short distances, F equals ma squared, and that would solve it all. So here's the part where I start giving my views. So back in 1983, a lot of us said, Morty, tell us more. Tell us something MOND predicts. And that's where I'm going to answer your question, is it a respected theory? So I would say it's not a theory. Theories make predictions and can be falsified. And so it just does not speak to me. It doesn't sound like the right theory, and it doesn't make predictions other than rotation curves. A theory not only explains existing phenomena, then it brings something new to the table that you can test. And so now I'm going to show you this slide that I showed in my talk. Let's see, big surprise would be no dark matter. If MOND is right, I'll eat my PowerPoint, laptop included. Okay, so let's see, who asked that question? Was that Gaz? Thank you very much for that question. That was great. Let's see, I got another question. Russell asks, could dark matter and dark energy exist in dimensions outside those we perceive? Could these phenomena coexist in a parallel brane and yet exert influence on our dimensions? And there have been scientific papers written on that, because I think what Russell is alluding to, he's putting together these ideas from string theory that there are extra dimensions, and we live on a membrane, and there are other membranes and out there, and so that is a possibility. But the reason I put this question right next to the Mon question is, tell me more. Tell me more. So that's the germ of a good idea, but tell me what it predicts so that I can falsify it. So the hallmark of science, as opposed to other endeavors, is things can be falsified. We're not just interested in really cool ideas. We're interested in how the universe works. And so Russell, they could exist in dimensions outside those perceived. And that's a really interesting idea, but we need to hear more about that. Let's see. A question from Joe about black holes that I can actually answer, because I'm not an expert on black holes. So the question about black holes is the following. If one black hole consumed another, does the resultant entity occupy a larger, smaller, or the same amount of space? Now, the amount of space occupied by a black hole is a very interesting question. Let's see, I lost my, oh, there's my cursor. And so I don't want to delve there, but I want to tell you what we do know. It's a very elegant, I can't remember if it was Penrose and Hawking who proved this theorem, that black holes, the best way to measure them is the area of their event horizon, because the amount of space inside a black hole is something that's hard to calculate. So what we can measure from the outside is the area of their event horizon. And so for a black hole the size of the sun, that would be a few square kilometers. So what we do know, and what's been proven, is that when two black holes come together, the area of their event horizon gets larger. And that's the only reliable measure that we have. Let's see. I'm going to go on to a couple more dark matter questions, and then we're going to turn to dark energy. I had a question here. Let's see. Where's my cursor going here? Okay. Question about dark matter detection. It's a really good one. Let me read it. It's from Joseph. And it comes back to this hallmark of science being the falsifiability. So we have this beautiful idea. How are we going to test it? So Joseph asks, underground detectors of dark matter particles rely on collisions between ordinary matter and dark matter particles, ordinary matter being atoms. What force mediates the interactions between the ordinary and the dark matter particles? So the truth of the matter is we're not 100% sure. But in some of the theories of dark matter, particularly the theories of dark matter where it's a supersymmetric particle, the force between them is a relative of the weak force. So if you remember the forces in nature, there's the strong force that holds quarks together and holds the neutrons and protons in the nucleus. There's the electromagnetic force, which is the greatest force in the world because it makes atoms and it makes us. And then there's the weak force, which is responsible for some of the nuclear decays, the decays of that change a neutron into a proton. And so that weak force, number one, is weak. That's how it got its name. And so the force that allows dark matter particles and ordinary matter particles or atoms to interact is the weak force. And that means we have to build very, very sensitive detectors, and that the event rates in them are very, very small. Rates of, by now, we've built some detectors, and we know the rates are less than about 1 per ton per day. So these dark matter particles are really shy because they don't interact via the electromagnetic force. And that's going to bring us to another question here um, about the difference between the electromagnetic force and the weak force. So it's probably the weak force, or certainly a force weaker than electromagnetism. So let me move on into this question about dark matter annihilations, because that's one of the ways uh, that we might detect dark matter, and we have a hint that maybe we have detected the dark matter particles. So this is from Colleen. How do we know that dark matter annihilates into positrons, and neutrinos, and gamma rays? Why not something else? So the answer to this one, let's see, I'm going to put a slide up here for you to see. So the answer to this one is not unlike the answer to the previous question. So again, since we don't know what the dark matter is, we don't know all the things that it can annihilate into. The reason that we focused on positrons, neutrinos, and gamma rays is that those are things we can actually detect. And some of the theories of dark matter, particularly the ones involving supersymmetry, say that it should annihilate into positrons, neutrinos, and gamma rays, as well, Colleen, as other particles. But these are the ones that we can detect. And so it's like the drunk who's looking for his keys. He goes over to the lamppost, not because that's where he thinks that he necessarily dropped the keys, but at least if they're there, he can see them. And so I want to show you a slide. I think I may have shown it. The Fermi Gamma Ray Space Telescope um, uh, can look for dark matter annihilations into gamma rays. And so one of our fellows here wrote a paper, or was a co-author of a paper about a year ago, um, saying that there was evidence for dark matter annihilations from the center of the galaxy. And so I've got two images up here. One image, the one on the left, is what the gamma ray sky looks like near the center of the galaxy. So let's see, I'm trying to see the scale here. This must be, there's 1 degree down there. So this must be about 10 degrees by 10 degrees. There's the center of the galaxy. Center of the galaxy has a lot of good stuff going on. Here's a pulsar. And now you take out all the stuff you know, and there's a whopping big, now we're over to the panel on the right, there's a whopping big signal left over. Very statistically significant. For those of you who know about statistics, 35 sigma. And so is that due to dark matter particles annihilating into gamma rays? And the short answer is we don't know. We know it's something other than the known sources. So it might be something new and exciting astrophysically going on at the center of the galaxy, or it might be dark matter. And so one of the ways to test this idea, I was just talking to Tim Linden, who's a fellow here who's been involved in this, and one way to test it is to go to a much less interesting galaxy than ours, dwarf galaxies, and a couple of new ones have been discovered by the Dark Energy Survey, where there's less astrophysics going on at the center, and see if you see that same glow. And so far they haven't seen it. So now I'm going to segue to a question about scientists are not supposed to play favorites. Oops, wrong side of the screen here. We're we're just about on what about the axion makes it a dark matter candidate. So the axion is absolutely my favorite particle because when I was a graduate student at Stanford, that's when two theorists at Stanford, Roberto Pache and Helen Quinn, invented it. And so there I am. I'm often called defender of the axion. And the stock on the axion has gone up recently for a couple of reasons. So the axion is very, very different than the WIMP. So the axion is very, very light, whereas the WIMP may weigh 100, 500 times that of the proton. The axion weighs a million times less than the electron. And it was put forward to solve a very subtle mathematical problem with the theory of the strong interactions. And so why do we think it could be the dark matter? When we calculate how many axions should be left over from the Big Bang, guess what? The answer is about the right number to be the dark matter. And then I've got this little fanciful slide here. Axions are so much fun. If that particle really exists, there's all kinds of fun astrophysics you can do, which I've shown in this slide here. So now, actually, I'm going to take a question. We're going to segue and start talking about dark energy. And Tom asks a really good question. Can you explain the pressure component of repulsive gravity again? So that's a really good question. And if you understand the answer to this, it's a really big deal. Let me see if I can find, I've got a slide here that I think may help us here. Yeah, here's the slide I want. So general relativity is a new way of thinking about gravity as space being curved. But we can also formulate it in the old language of pushes and pulls, and sometimes that's a useful way to look at it. And it makes it easier to compare with Newton's theory of gravity. And so here's the amazing thing. Here's the amazing thing about how dark energy causes repulsive gravity. So in Newton's theory, actually Newton's theory in some ways is much more amazing than Einstein's theory, because in Newton's theory, the gravity field of an object only depends upon its mass or its energy. Those are equivalent, E equals mc squared. So, and I remember learning that, and I never really said, wow, that's really weird. You mean it doesn't really matter what it's made out of? Its gravity field only depends on its mass. In Einstein's theory, if you think about it as a push or a pull, then what sources gravity, what causes the gravitational field of something is, I'm pointing here towards rho, that's the amount of mass. And then it's rho plus 3 times the pressure. So it does depend upon what the stuff is made out of. And so, for example, let's just use the sun. The sun is really hot. The pressure is really, really big. And so the sun has a slightly stronger gravitational field than a cold version of the sun that didn't have pressure, that didn't have those nuclear fuels. So once you buy this, and this has been verified by experiment, now you have something really interesting. Because pressure, the pressure of a gas, which is just the gas pushing out, is positive. So it just says Newtonian gravity is stronger. And by the way, this plus 3p is what makes black holes. Maybe we'll come back to that later. Pressure can be negative. Something can be elastic. A rubber band is elastic. And so that's just negative pressure. And so if you have something that's extraordinarily elastic, so with a pressure more negative than a third of its energy density, then rho plus 3p is negative. And so gravity, instead of being attractive, is repulsive. And that's what's happening with dark energy, we think. And so right over here on the slide, I've put for the energy of the vacuum, or Einstein's cosmological constant, P is equal to minus rho. So let's plug that in over here. So we have rho plus 3P. P is equal to minus rho. So therefore, what's causing the gravity is minus 2 rho. So that negative pressure is really a big deal. And actually, I probably don't want to bring this up, but I will bring it up. So I'm the guy who named dark energy. And one of my colleagues, a good friend, Sean Carroll, said, "Oh, Michael, that's a really bad name because what it's really all about is the pressure. You shouldn't call it dark energy. You should call it negative pressure, I think. But dark energy won, and I think it's a cooler name." Okay, so we have another question that came in here from Simon, who asks, which is stronger, gravity or dark energy? If dark energy is stronger, why doesn't everything just fly apart? Or are we doing exactly that very slowly? So let me unpack that. So which is stronger, gravity or dark energy? So dark energy is not a force. So dark energy is stuff, and it has repulsive gravity. And this is one of my hobby horses. So I've been the enforcer on this idea since early on, that whenever a reporter asks me, what about that new force called dark energy? I say, no, it's stuff with repulsive gravity. So what's causing the universe to speed up is the repulsive force of dark energy. Now let me keep going with this question. So why doesn't everything just fly apart? Well, the universe is flying apart. So dark energy is running things now. So dark energy is running the universe right now. Let's see if I can find this slide that I showed you in New York. Maybe I don't have it here. Let's see if I have the... I can't find it. So dark energy is running the show now. And unless it dissipates, unless it's slowly decreasing with time, right now our best evidence is the energy density of dark energy doesn't change with time. Let's suppose it were slowly decreasing and went away, then the universe could slow down. But as long as dark energy is there, it's going to be speeding up. And I guess I'm going to do the full Monty here on Simon's question. If the dark energy is really weird stuff, if its energy density is increasing with time slightly, then the effect of dark energy gets even stronger. And so eventually, let me just back up for a second. I apologize for this. What I meant to say is that if it's just the energy of the vacuum, indeed the universe keeps flying apart, but objects within it stay bound. Clusters stay together, galaxies stay together. But if the dark energy slowly increases and builds up with time, eventually dark energy will rip apart clusters and then galaxies and then solar systems and then the sun and the earth and us and so on and so forth. Let's see. Oh, Dan, so we're getting close to closing time here. No, maybe we have 15 minutes, but we're getting into the philosophical questions, my favorite. So Dan asks, do you see a future when particle physics is so well understood that everything is known about every possible fundamental particle? Or do you think there will always be mystery particles that get found or proven? And, oh my goodness, Dan, this is a very rich question. And for those of you who want to hear a much better answer to it, I suggest that you go find Feynman's book, The Character of Physical Law. I'm looking at my bookshelf, which you can't see. I'm not going to find that book right away. I'd love to just bring it right over here and show it to you. And he addresses this question. And it's a really good question because the question is essentially, will we ever discover all the laws of physics? And if we do, what will happen? And Feynman was worried that if we did, then it would fall to the philosophers to start trying to explain the laws, and that there would be a real degeneration. Because what we do um, in trying to discover the laws, it's that falsifiability. So we got Brian Greene and all the string theorists saying they're extra dimensions, and things are made out of strings, and that's a terrific idea. It's a wonderful idea, uh, but the real question in physics is that how nature works. And so, if you knew all the physical laws, you would end up kind of arguing where did they come from, and that's something that's very hard to prove. And so things would degenerate. Ooh, I'm probably going to get philosophers mad. Degenerate into philosophy. Often in physics, the way I think of physics, what we do in particle physics is we're like a little kid watching a chess game. There we're watching the chess game, and we're trying to figure out the rules. We're trying to figure out how the pieces move, and here we are in the universe trying to figure out, how things work. And imagine that you're doing that with a chess game, and eventually, when you figure out all the rules, you start saying, "Well, where did those rules come from?" And of course, now it becomes historical. So that's part of the answer. And again, I recommend you go read the final chapter of The Character of Physical Law by one of my heroes, Richard Feynman. The other part of it, which is more emotional and passion, is that we have so much fun trying to figure out how the universe works that we cannot imagine that future generations of scientists wouldn't have that same fun. And of course, the more you know, uh, I'll work in an old saw here. The more you know, the more you realize how much you don't know. And then I want to end by, because I bet there's some people, one of the things I learned uh, in being president of the American Physical Society is appreciation for science other than my own. So even though cosmology is by far the most interesting branch of physics, it turns out other people do some pretty interesting things. And so even if we knew all the rules, and I'm going to go back to the chess game here, even if we knew all the rules, we wouldn't be done. I know all the rules of chess, and I know nothing about the chess because I know nothing about the game of chess because knowing all the rules doesn't mean that you know all the games that can be played. And in condensed matter physics, all the rules of the game for how matter behaves and how material behaves, those have been known for 100 years. It's quantum mechanics, it's electromagnetism, and we're still creating new materials and exotic phases of matter and new puzzles. So even if we knew all the rules, there'd still be a lot to do. Let's see, I saw two more philosophical questions that I got that were really fun. Um, let's see, one was from Kramer, and I'm watching the clock here a little bit because I want to leave time I've got the perfect question to end on. But first, Kramer. What are the most interesting challenges you face today in your research? Um, the three things that get me up in the morning, that get me out of bed, are dark matter, dark energy, and inflation. And let me rattle those off one by one. So dark matter. This is a puzzle that's been around a little over 70 years now. Almost 75 years. See if I could do math in my head a little better. So 33 is when Zwicky first saw dark matter, so actually 82 years. Somebody check that. I hope it's 82 years. Um, and we think we're in end game. We have a compelling idea, and compelling doesn't mean right, and that's that dark matter is a new particle of nature. And we've got three ways to detect it. Produce it at the LHC, large underground detector, detect the annihilations. And it could be, while I am living, that the dark matter problem is closed out. And I'm really hoping for the triple solution where we make them at the LHC and bottle them. We detect their annihilations in our halo, and we also detect them with one of these very sensitive underground detectors, so that I can go to Missouri and convince people that they, that we really, that this outrageous claim that most of the matter in the universe is something other than we're made out of. So that's dark matter. Dark energy is very different. We're near the start. We're near the start. We don't have any compelling ideas. This is a true puzzle, and it could be that once I'm done with this master class, I'll get some quiet time here and I'll solve it in the next hour. I wouldn't bet that much money on it. It could be that it will get solved by some of my students. That would be fantastic. It could be that it gets solved by some of the young people that I've met in various venues, high school students or even younger students who come to my lectures. Or it could be that this is a problem that was accidentally discovered. It's a problem that won't get solved till the 23rd century. Let's see if I can do my math right. 23rd century, that would be about 200 years. But we discovered the puzzle in the, got to get this right, the 20th century, at the end of the 20th century. So we don't really know. And that's a different kind of fun. You don't know when the breakthrough is coming. And then inflation, that one's, I don't want to tread on Andre and Alan Guth's territory, but last June, we were all pretty excited that we might have detected the signature of the gravity waves produced by inflation. And that would have been a giant leap forward. We're less convinced of that now, although we've got to follow that up with more sensitive detectors. And so inflation is one of those things where we have some very good ideas about it. We have the ability to test it, and we're making progress, slow, steady progress. So let's see. For my last question here, unless somebody tweets or sends something in here, I'm going to go to where is this one? Ishan. I hope I'm pronouncing your name right. What do you think the ultimate fate of the universe will be? Boy, that's a really hard question. That is a really hard question. It's an interesting one because, again, what I think doesn't matter, because this is all about how nature is. And I know people have very strong feelings about it. So, for example, Freeman Dyson, who's a name that I think many people have heard of, it's probably been 40 or 50 years ago, wrote a paper in Reviews of Modern Physics on the ultimate fate of the universe. And if the universe keeps expanding the way it is now, its ultimate fate, there's no other word than dismal. Eventually all the stars burn out. Actually, something happens before then. If it keeps accelerating in about 100 billion years, we will only, the sky will darken galaxy-wise, and we'll only be able to see a handful of galaxies in the sky. The ones that are part of the Virgo cluster will become part of the Virgo cluster. The rest of the universe will, as they say, fade to red. And so that won't be very good. It's really interesting if we've forgotten everything we learned about cosmology and have to rediscover it. It might be very hard to rediscover because the microwave background will be so faint we won't be able to detect it. We'll only see the galaxies in the Virgo cluster, and therefore we won't see the expansion of the universe. Hopefully, we won't have to rediscover the universe. Um, then that's only 100 billion years. And this is the crux of an argument that I've tried to take to Congress. It hasn't worked so well so far, which is now is the time to do cosmology because in 100 billion years from now, the sky is going to darken and we're not going to be able to see other galaxies. But it gets worse. Stars, once they use up all their nuclear fuel, they no longer shine. And so, something like 1 trillion years from now, all the stars will be gone. All the stars will be gone. And so, it'll be a very dark place. Um, that's 1 trillion years from now, just the blink of an eye. Um, then you have to start thinking about, well, okay, the stars are gone, but, we're using some of Penrose's clever ideas to generate energy from spinning black holes or something. So the question is, can sentient beings, can intelligence continue? And that's where I recommend that you look at Dyson's article. So this has been a big issue. Intelligent beings require energy, and in this ever-expanding universe, energy becomes more scarce. Free energy becomes more scarce. And Dyson had the idea that maybe you could take long. He realized that you couldn't. These sentient beings couldn't think continuously. They'd have to take naps. Um, but even that doesn't work. And so it's a very, very, the universe ends with a whimper. And so that's why a lot of people like, and I'm going to use the word like, a non-scientific word, like a cyclic universe. Like, what if it recollapsed, bounced, and started all over again? But again, it doesn't really matter what I think or what others think, because science is all about, what uh, nature thinks, and the laws of physics that we're presented with, not the laws of physics that we would like. Um, Time has really gone by quickly here, and I kind of timed this perfectly, ending on this philosophical note uh, about the universe, how it might end. Of course, an equally interesting one that I could have been asked about, I didn't get asked about, is how the universe began. That's a question that's now within the realm of science. Um, so I've really, really enjoyed uh, this master class on the dark side of the universe. Your questions were terrific. They allowed me to give an impromptu lecture combined with real facts and a few opinions. Please pay attention to the real facts and ignore the opinions. So thank you and goodbye.